Hello everybody, I'm Basti. I work on FutureSDR, a software-defined radio runtime implemented in Rust. One of its features is that it's working with WebAssembly, and that means you can run a FutureSDR's SDR application completely in the browser, even interfacing hardware through WebUSB. So in the past, this was only possible, but what we did was the C driver was cross-compiled to WebAssembly with a patched version of mscripten and a shim layer that adapted libUSB to WebUSB. And then you had one mscript module with a driver, then I had another WebAssembly module with the Rust implementation for FutureSDR, and then everything was glued together with JavaScript. And it was really amazing to have this proof of concept, see what the technology can do and play around with it, but it was in no way a good developer experience. So I spent the last 1.5 days to restructure it a bit, to try different options. And now I think I come to a version where it's really fun to work with WebAssembly-based FutureSDR applications. And this is what I want to show you today. In this video, we will go and step through the process of kind of adapting a native implementation of a Zigbee receiver to run in the browser. And to show you what you can do is get a bit of an idea of the development process, see the developer experience, and hopefully this is something that you find interesting and can then adapt the same thing to other projects, other receiver, transceiver implementations. Okay, so in this video, we'll use the HackerF, which is a USB-based SDR that will then interface from the browser. And to generate some Zigbee frames, I have an 80 USB from the Sysmacom store. It's an USB-based Zigbee transceiver. But the coolest thing about it is that it's well supported by Linux. So can do IWPAN list, and we see this thing is here connected. It's on channel 26 on 2.48 gigahertz, and I have a Scapy script, projects Zigbee, where I can just generate some frames. So this is generating Zigbee frames with a payload FutureSDR and some sequence number. And there's some pan IDs, just adding some default headers and sending it out through this USB-based transceiver. So we can keep this running for the rest of the video, move it there, and then go to FutureSDR. So FutureSDR comes with several examples. One of them is a Zigbee receiver, so Zigbee, WLAN, ADSB, some stuff comes with just as examples, and we can just run them. And we see here, I didn't adjust the gain, so can put it to the antenna. So we are receiving Zigbee frames. This is now a native implementation running on my PC, so it's compiled, natively running code. So this is the base. So this is what you get when you download FutureSDR. No big hassle with installing the module and whatever, just working, or just rather straightforward to get it to run. Okay, the rest of the video will now try to get this same thing running in the browser. And let's see if we manage to do this. If you want to develop on your machine for WebAssembly, you obviously need the tools to cross-compile for the target. And if you have Rust installed, you can target list. You see a list of all targets. I already have it installed. It's the relevant target for us is WASM32 unknown. So you'd do target add, and then this WASM unknown. I already got this. The first thing you need. Second thing you need is cargo install trunk. Trunk is a project or a tool that's giving you a nice developer experience. What it does is it takes a Rust project, it can cross-compile it to WebAssembly, packaging up in a module, integrating the module in a website, serve the website with all its assets on a development server with live reload and everything. So this is, I think, as good as it gets for a developer experience. Okay, so we have these things installed. Now, obviously, first thing is we have to configure trunk. And I don't know it very well, but there are some examples on the website, and we basically need two files, a trunk toml file and it just tells us that there's an index.html file, which is the base for the website that we're serving, and that should use the dist folder to put all the assets in and then serve this through the dev server. first thing. And then obviously we need this index.html file. And there's also an example here. And you can just copy it. And if you already use some JavaScript packaging tools, very similar, you have this special tags. Now that's telling trunk, for example, that you should use tailwind, and there is this file, and to process these assets and put it in the dist directory and serve it through the dev folder and do some processing of these assets. We don't need this tailwind. We don't need to copy files. What we probably want is a favicon so that the website looks nice. So let's just add one. And anyway, we need some assets folder sooner or later anyway, I would say. And then the second thing, let's add a title. FutureSDR, the receiver. Okay, so far so good. And I don't know, obviously we need the, have to create this assets folder. And I prepared a favicon. You can copy over. Okay, so now, yeah, we already have trunk here running, and it's trying to now build it. So what I did here in this terminal to tell you is trunk serve. And now it is trying to compile the native implementation. So the native receiver implementation, we can go and see, it should be source bin tx, source rx, and whatever. So it's trying to build the native binaries for WebAssembly, but obviously that doesn't work. So we have to create one that's specific for WebAssembly. So source bin, let's call it WASM-rx, I would say. And here add an empty main function. And I need to go to the index.html file. And now we have to tell trunk, so how to process, how to deal with this Rust stuff. We can go on the website, because currently it doesn't know which binary to build, or tries to build all the binaries or whatever. So we have to tell it that how our binary is called. And before this, we have the Rust asset type, and we can tell it data bin, data binary, how the binary is called. So we can say Rust data bin equals wasm-rx, and then save this and see. Okay, now it did something. It probably and hopefully compiled the empty binary. I mean, we won't see anything, but there's something that is served. Let's check if everything's working. We can say here hello, and it's popping up as a live dev server with reloading. Okay, so far so good. So we have already a trunk setup. It's already compiling the WebAssembly, but it's not doing anything. And we could now go and extend this website. But obviously we don't want to extend this website. What we want to do is do everything in Rust. And now we could, in theory, already start implementing our FutureSDR receiver in this main file. But the problem is this, that with WebUSB, there's some constraints for security reasons, probably, or I don't know what, that when you load the site, you cannot immediately just run WebUSB stuff. All of this WebUSB stuff has to be triggered by some kind of user interaction. So you can't just go on a website and it will start using your USB hardware. You always have to somehow trigger it as the user. That means we need basically a button with start to start our FutureSDR receiver. So sooner or later anyway, if you want to develop some stuff for the web, you need a web framework. And the best one, so I tried several, and the only one I somehow was able to use a tiny bit is Leptos. And Leptos is a framework with fine-grained reactivity. That's how they call it, I guess. And or you can just copy also from their from their website. So we don't have it in the path. We will just, what's the most recent version? 045. Yeah. And with laptops, there's one thing to say is that most important thing is that I would recommend to use it with nightly build of Rust. So with Rust, you can configure if you want to use stable or nightly. So Rust up default, and I use nightly by default. And especially if you're working with laptops, I would recommend to do this because it has some really nice features. So if you want to look into it, to use to read documentation to get more information on it, but in this video I will use the nightly Rust toolchain with the nightly features that Laptos has. And yeah, the other stuff are not really important. Log is the logging crate in this also, but we also ship this or re-export this as part of FutureSDR. And yeah, now I've seen I added dependencies that are specific to WebAssembly. And in Cargo, so with Rust, you can say you can have dependencies depending on the compile target. So we can never can remember how this is the syntax, but it's working like this. So we can say these dependencies are only relevant if you do not use WebAssembly, and these dependencies are only relevant if you use WebAssembly. Obviously, we also need FutureSDR, but in this case, we don't need SciFi. So I hope at a later point, SciFi, which is the hardware abstraction layer for FutureSDR, will also support this WASM stuff. But since I just was working on it, I have the hardware driver now as part of FutureSDR encapsulated in a block, and it's not part of SciFi. I hope in the future that the SciFi, the hardware abstraction layer for software-defined radios, will also support WebAssembly. So I have to move this implementation over to SciFi and then interface it through SciFi. So it shouldn't be a big deal, but since the web everything is async, and currently SciFi is not async, I first have to come up with a good way to combine async and non-async drivers in one module. So this is something that needs a bit further thought. For now, this HackRF driver is just a normal FutureSDR block that is specific to WebAssembly, so we don't need SciFi. Okay, so we have FutureSDR, we have laptops, we have the console log. Hopefully this should then compile again. Okay, so this is still there, but obviously it doesn't show anything. We can now go to laptops and just copy paste, continue to copy paste from the examples. I think they have a example with a simple counter. I can just copy this over to our WASM RX. So copy this over and copy the main function over. So we don't need this. This is already at the top. And then there's a new main function. And there's a laptos. They call it components. In this case, maybe not destroy it yet. That is now here, and the rest should be more or less okay-ish. Now you see everything is red, and this is because my language server is trying to compile it for natively, and obviously that doesn't work. To compile this WebAssembly framework natively. So I have to tell my language server to somehow cross-compile for WebAssembly. I don't know how to configure this, so what I usually do is in the cargo config file for the project, I just add a default target. Now it says by default, use this target. And then my language server seems to pick it up. So this is one thing. And the other thing, and this is important, and this is some non-obvious stuff that you should know about, is that compiling a FutureSDR or most applications to WebAssembly, you have to use some special Rust flags. And I figured these ones out. They are not specific to the project. So you can just copy paste them, and it's telling them if you compile for the WebAssembly target, add by default these compile flags, and this used for WebSys unstable APIs. So the WebUSB is still not a stable API, so you have to tell it to explicitly tell it to actually use these APIs. And all the other parameters, they are to increase the memory size of the WebAssembly module, because this is a non-typical WebAssembly application, and the stack size and the whole memory size is by default smaller. So I just added big numbers here, just with but trial and error, but it should give you all these parameters that you need, and I think I picked them pretty big, so you shouldn't have to adapt them. So, but it's important to know. So if you start a WebAssembly project, go to copy paste this from this project, or at least here look at the compile flags if you see some out of memory errors or stuff like this. So very important. Now if we restart our editor, let's see if things are getting better. Let's see. I think there are some logging output. Oh yeah. Now the language server works. It's telling us that we don't have this log crate because I deleted it from the dependencies. As I said, this is re-exported from FutureSDR, so hopefully this should work. Now it compiles something, and here we have a web application with the counter. So we have buttons, and it's reacting, and it's doing something. I have not a good idea of how this is working, but anyway, we can just say we don't need a simple counter. We just need a GUI. Can say h1 hello world. And just call it GUI. And then we mount this as GUI. We have no parameters. Simplest thing, probably. Do we now have hello world? Yeah, now we have hello world. Okay. Now, as I said, yeah, we need a button. Button. And what we want to do is start it. And so that's a big start button that you have to press. That's a user interaction to start the flow graph and to allow it to interface WebUSB hardware. Okay, so we need a start button, and the start button has a on-click handler. Let's just call it click. And now if we can create a closure click. And just output something clicked. Things compiling. Okay, so now we start. Okay, then it's setting in the CV. It says it's logging clicked. So this is working. And now we can basically start and try to copy over the flow graph, because now we have something that's clicked, and it should then just run a function. So basically what we do is we create an async function, run flow graph. That's not doing anything, but they should run the flow graph. And async function. Now we can go to Zigbee bin rx and just copy all of this over to here. So now this is the Zigbee. Now it's looking ugly because this is a lot of compile errors, but in essence this is the Zigbee FutureSDR receiver. So let's try to clean this up a bit. So the clap stuff is for parsing command line arguments. We don't have command line arguments. Blob to UDP, we don't have UDP in the browser. Just delete it. This here is all the command line arguments. Delete it. Yeah. Then we have the FutureSDR receiver here. This at the bottom here is UDP. We don't have this. And we can only we cannot run it synchronously and block in the browser, so we only have a run async function that we can await and important thing is this function here is then an async function, and how do we call it? Run flow graph inner, and here we just do run flow graph inner. Wait. Yeah. So, and why I add this kind of indirection of run flow graph inner and run flow graph is that this one here returns a result. So we have this result and can everywhere for error checking just use this question mark operators that you might know from Rust. And so we can use them here, but the function that we can run here, it is not allowed to return command line arguments. So we kind of wrap this function, and we can even kind of consider or print out the return value. FD returned. Okay. And here at the bottom is then the actual function. And here we have the SciFi source. And as I already mentioned, SciFi source, we don't have SciFi here. So we have to build our own source. We have to use the HackerF source. This is the one WebAssembly specific driver that's now part of FutureSDR, and that hopefully in the near future moves over to SciFi, so that we don't even have to make this kind of replacement, that the SciFi then also, the SciFi module supports WebAssembly based drivers. Okay, but for now we have to do it, and we have to add this block. And hackrf like this. Yeah, SciFi, we don't have this. Parse channel was also for the command line arguments. And then, yeah, this seems to be happy. So deleted some stuff, replaced the source. And yeah, now the thing, we have to start it from here. So that means, oops. Let's keep the clicked for now. And here now we have to run the function, which is an async function, but we are here in a normal closure, so we cannot run do just async await. And for WebAssembly, in Rust, there's a clade which is called WASM bind futures, I guess. Yeah, exactly. So we have to add this to our dependencies. And then we can do WASM bind futures spawn local. How's it called? Run flow graph. Does this compile? No, it doesn't. WASM bind futures. Our language server is still lagging behind. I think it's still rebuilding in the background. Okay, now comes the big moment. This is already, yeah, click start. Oh, look, we got a frame. And we can put it closer to the antenna, and then we see, okay, the receiver is running in WebAssembly. Somewhere here it's receiving some frames. The CPU usage is quite high, and all of this is because when we do trunk serve, it's doing a debug build. We can also tell it to make a release build. This will now, okay, faster than I expected. The WASM opt is now running in every build step, which takes a few seconds. But yeah, now it's running. And yeah, okay, now we see the CPU goes down, but also we don't see anything. Reason is this logging to the command line is a debug output, and debug is not compiled in release mode. So let's go ZigBee. It's in the Mac protocol. The thing we've seen, I guess, is debug received frame CRC correct. Let's just make this an info of the log level, which is not compiled out, which is also not imported here. let's see. Success. Start. Okay, now it's receiving more frames. Okay, but it's now not locking every line, which is kind of merging the lines. You see CPU usage got down, and now the whole FutureSDR receiver is running in the browser. So that was, I think, rather straightforward. Now we could stop here and say, okay, in theory, the problem is solved, but I want to show you how you could now go ahead and try to build a nice GUI, or how you can now interact between these GUI domain and the FutureSDR domain, and how you can basically communicate back and forth and create nice GUIs. Okay, so let's continue. I think what we obviously, so we can just here say it, disconnect the USB, then it will stop, save some CPU. Okay, here we can also go back, say, yeah, just do this as debug anymore, because now obviously the next step is that we want to, our WASM receiver, it should kind of get this received data out and push it into our GUI domain. So what we need to do here is, or what we can do is, we can add a block to the flow graph. FutureSDR comes with some blocks for messages. One of them for message passing, one of them is the message pipe block. There's really push received messages into a channel. Well, perfect documentation. Basically, it has a message input handler, and you can then give it a channel object, and it will only get the messages from the input handler and push it into the channel. So we can, when we create the flow graph, create a channel, we keep the reading half of it, push the write half of it into the message handler, and it will then push all those messages into the channel, and we outside of the flow graph can then just read from this channel and receive all these messages. So let me show what I mean by this. I mean, this message pipe block, we can add it, but yeah, the easiest way is probably just look where it is used and then copy paste from it. So the wireless LAN receiver uses it. It looks like it, at least. So just copy it. We have to import the message pipe, the MPSC channel, and I guess also this PMT type. So let's get some imports from here. So these two and the PMT. It's not happy with me. The message pipe block. Okay, that's looking better. Okay, so we now have this message pipe block. We have to connect it to the flow graph. How's it called? Message pipe. Oh, good. Message pipe in. Okay, so we have a block that is now getting the messages. Now, instead of just running the flow graph and blocking, we just want to start the flow graph and listen on this channel endlessly to wait for the received messages. You can also copy paste this from the other example to avoid fiddling around. So in this case, I have a runtime. When we start, we have no sync because we are in the browser. There, everything is async. We await this until the flow graph is started. We get these two handles. We also don't need this because we are in an async function. This is then receiving. So this is the RX frame, is the receive handle of this channel. It's waiting for data to be received there and then printing it out, which also doesn't work in the browser. So we have to do info instead. Is this imported here? Ah. So this one is structured a bit differently. Info, now I import it. SDR log info. Okay, it's doing something, and ideally it should now again print the received frames on the terminal. So let's start the receiver again. Connect HackRF1, received frames, so and so many bytes. This is this output. So now we have a FutureSDR receiver running in the browser that is getting the received message out in this through this channel object and reading from it. And obviously now we have to, in this handler, when it receives a message, it should now push these things to the GUI, to the Leptos GUI. And for this, I think in Leptos we have signals, which it's kind of like global variables where you have a getter and a setter, and when you update the value, all the getters will be notified, and selectively only the stuff that depends on these getters is re-rendered. So it doesn't just re-render whole components or whatever, but it keeps track on when it renders a component, which getters or signal getters are relevant for this part, and only then if this the underlying signal or global variable changes, it will only update this specific part of the DOM, so to say. So this is what they mean with fine-grained reactivity, because this few function here is just run once, and then everything is run only once again if there's really something that changes. And we now have to implement basically this signal mechanism, and to first of all have this global variable where all these received frames are in, and have the GUI get re-rendered once we receive a new frame. That's the rough idea. So let's go. Standard collections DQ. I think, vec DQ, I think it's called, because I want to have a linked list to allow it pushing in new frames at the front, and then if it's longer than 20 frames or so, just pop at the back, so that we can kind of just move frames in. With a normal vector, this is not really nice to do. But this is kind of more like a linked list as far as I understand. Okay, so we have this vec_dq, and now here we have to extend this view with a Leptos signal. So a signal is always a getter, let's say frames and set frames. And it's create, and now it would be great if my language server worked. Create signal context vec dq new. And let's see if this creates signal. Yeah, this is what I mean with I need my language server. Let's see if it comes back. So we have this create signal, and as I said, we need to pass the set half, so the part that can update this list of received frames. We should push this down to our FutureSDR receiver. So we tell him, okay, it's a set frames. This is the things we pass down, and the set frames is a write signal of a vec dq with a vec u8. I mean, we have to think about how we want to represent the frames and where we want to parse them. But when you receive the frames, they are a vector of bytes. So at the moment, this is would be a vector of bytes. Let's just start with this, and probably good enough. So I have to add this parameter here and here, and have to pass it down. Okay. So now we can do here, we can do set frames dot update f, and then say f push front data. Okay. Still no language server. Okay, so I'll make a break, fix my language server, and then come back. Okay, I don't know what happened, but something happened, and now it seems to work again. Okay, so where did we stop? We said we tried to update a signal, pushing the frames into this signal. So we have set frames, and we want to update the underlying vectq and push front the data into it. And then here, here we set this up. What does it say? Value is captured, the frames. If something doesn't work with laptops, you usually want to move stuff into the closure. So now we moved it into the closure, and that already seemed to have done the trick. So we have these frames, and currently we don't read it. So now we want to iterate over this. We want to iterate over these frames. So let's see how this is done with laptops. I think laptops dev is the website. There are some documents. I think there's a section on how to iter over stuff. Iteration. Values into iter, map, collect. This is perfect. Let's see if we figure out how to use it. So we want to have a list with all these values. The values are the frames in our case. Into iter for every, let's call it F, for every frame, we just do N. I don't know, does it maybe just work? So it's not really frames into iter, read signal. Do I have to get them? Is this required? Now we have a list of frames. Okay, let's see. I think this is not working yet. So let's start. Okay, we receive frames. It doesn't fill a list. I think in this case we have to make a closure out of it. Because N, F, it's called. So now working. Is it now happy? Also not happy. Borrowed value doesn't live long enough. Okay, as I said, if laptop's not happy, then move. Looks better. Let's see what's happening now. Okay. Okay, interesting. That's the way it's plotting values. So now we have this frames. We have them in laptops. We have them in the GUI. I think it's adding new frames at the top. Probably not the nicest way to look into it, but it works, and we have a GUI. We don't have to look at the terminal anymore. And you see how they can push the frames into the GUI. And now I would say just make some smaller changes. We can now say push front, and if flen 20 f pop back. So that means we always push to the front. When we then iterate over it, then we have the newest frames on the top. And so this should be working. And I think we can try to make a trivial or a very simple parser, let's say, for the frames that we don't have to deal with because we don't see anything from these values. Struct frame. Let's only say we want the payload extracted as a string. And so, and we have the frame. We want to have the payload as a string, and we create a frame. from the data payload. That is vec u8, and then we return a self, and so that would be self payload is a string from utf8 lossy, and then say data, and now the index, I don't know, 7 to, I don't know, data len -2 should be correct, I think. Because at the back there's 2 bytes of CRC, so it should go until there. I don't know where the data payload starts in this case. Let's maybe this is string from lossy. What does it say? Can't read it. Okay. And now we can push front data, and we can do frame new from the data. So we create a frame out of the data, and now just adapt this vecDQ to be a vecDQ of type frame. Frame. Where's the other one? Frame. Is it compiling? Now we try to print it, but because that's what. So let's derive debug. Does this do? Does it a debug print? Or do we need a? Does it need a proper display? I think it has to be clone as well. Is it now happy? And if you use the field only to in a debug print, it seems like that doesn't count for Rust that it is used. Just let's avoid this warning. That's a bit annoying. Allow it for the struct. So let's see. Go. So we have a frame payload. Oh, was even the offset was correct. That's cool. Okay, now we see we have a list of frames now. Pretty cool. So now this is one direction. So we had from FutureSDR, we get something out, we get it into the GUI, we even have it parsed. We can now make a full table for this struct. I mean, we can parse out the pan ID and all this other stuff and present it to the user in some nice way. So we now have one direction. So this was from the FutureSDR receiver to the GUI part. And now we want to do the other way around, and the only example I could come up is to change the channel. So we change the frequency of it. And for this we need some like a selector input and leptos, and just based on the selector we change the frequency. So we basically want to communicate now with the flow graph. Through the GUI we want to reconfigure the flow graph. This is the next thing we want to do. So first of all, what do we need for leptos? I think where's this FutureSDR? I think currently the code that is pushed on GitHub, because what I'm showing now is not yet pushed to GitHub main. I think there's already an example of the old way of doing it, and this includes, I think, also a selector for the channel ID. Oh yeah, this looks good. Div channel select. Yeah, okay. So we can save us this hassle. We can add a selector to our GUI. So there's the button, and then we add the GUI to select the channel. Still have to tell my editor how this stuff should be formatted. Let's see if this is already providing us something. I guess it should in some way show up. I mean, not do anything, but yeah. Okay, now we have this channel selector on this side. Now there's only the question of how do we now interface this thing from let's keep the 26 as the default so that we don't have to, in the beginning, always change it. Now the only question is we need a callback for this thing. So this is a form, and I guess there's the on change. So we have to do another callback. Oops. Change. And we say changed. Then we should get here a callback when this input changes. And then what we need is a way to get the new value from this thing, and select ref. Then we need from lapdos a node ref. I have no idea. At least Laptos has good documentation, so this is very easy to do. Okay, so let's say, because the thing is this, if you wonder. So if we do this, I guess it should work that we get a change event. Yeah, so you can see this. It works that we can see what changed, so this is good. But as far as I know, there's no way from this thing that we get here. I mean, there's an event that we get from this handler to get the value, or at least I couldn't figure out a way how to get the value out from this thing. So the only thing I could come up with, lapdos HTML select, is to say, okay, we create a node ref, and the node ref is kind of a reference to a DOM element. And so instead of trying to get the new value out of this event that we receive here, we're just asking the element directly. And no, I don't know how it's working. If this is the right way to do it. So at this point, it's just basically creating a pointer, the reference to it. Once it is rendered, the reference will point to the select element, and then we can and the callback is only fired when the select element exists. So that means we can access the select element here, and then I guess it has a value which gives us a string, and then we can try to parse. Now I don't know if everything of this is correct, but let's see. Let frequency equals frequency. Does this work? Don't see big complaints. And now we got we kind of get the frequency here out from this element. So we save select ref, so the reference points to the select element. We get the value, we parse it as a U64. I mean, these are valid U64 values, so this should always work. And so we have the new frequency. One part of it. So we have the GUI part. Now it comes the tricky part. We have to get some handle from FutureSDR to interact with the flow graph. If you know FutureSDR, it always has these handles. So the handle gives you a struct which you can interact with to get data from the flow graph, to call back methods from blocks, to get information about the structure of the flow graph. So you can do a lot of stuff with a handle, and the whole interaction if you are on in the same memory space as the flow graph and the same binary, basically, you interact with a handle. If you are from the outside, basically the same thing you can do with a handle, you can also do through the REST API. But obviously, if you run in the browser, we don't spawn a web server with the REST API. Doesn't make any sense. In this case, we just have a handle, and now we have to pass the handle to our GUI. And then once our GUI has access to the handle, it can always use the handle and update stuff through the handle. So we make another signal, so we can handle and set handle. And yeah, in the beginning, it always has to have a valid value. So we cannot say it's unset, so we have to make the handle an option of a handle, because in the beginning it has to be empty, basically it's none. And we do the same thing again, so we pass this one down, set handle. So we do set handle here and pass it down to our functions. So we do the same thing. Set handle is also a write signal of option flow graph handle. And do this here. And I guess further up it complained because we didn't do this nice. So yeah, let's just keep it like this. Does it compile? Not. So this looks okay. Here we have to then set handle, pass it down. A flow graph handle we didn't import. Runtime. I thought it's already there. Okay. And here then once it is started, we say set handle some handle. So we pass the flow graph handle basically into this global object where it can then also be accessed by the GUI. And now we did some major bullshit, or what? Oh god, what is this? Cannot find flow graph handle in this scope. Did I not? Did I misspell it? Flow? Oh. And obviously okay, now it seems to work. So we got a flow graph handle. And let's just do something fun in the handle get unwrap description. Okay, that is an async function. So we can have to spawn this. So let's just create an async context. Wait, unwrap, like there's no tomorrow. Description in so that was quite a bit, I expected. Okay, we don't use this is fine. Must outlive static async move. Can we move it in? Okay. So now what this does is, so now since we have a flow graph handle, we can interact with the running flow graph and ask it like, what's to get a flow graph description is what it's called. So run the description function. Now I'm really wondering what's happening. Oh, I didn't want to start actually. Anyway. Okay. When we change, we get a flow graph description. So the flow graph, if you look at this is basically JSON serialized how the flow graph looks. So there are the HackerF block. There are what other blocks? A Mac block. There's a message pipe block. So you get a whole description, JSON parser description of how this block looks like. Since we know the HackerF, what we can also now do is call callbacks of blocks. And for example, the HackerF block has a block to set has a callback to set the frequency. Okay, so now instead of getting the description of the flow graph, we will now call the set frequency method of the HackerF block of the flow graph. Hope this was more or less clear, very well phrased, very badly phrased. Anyway, so we don't want to do this. That was just to show you that you can now interact with the flow graph in any way you want. Let's say now we want to say handle handle get call. Now I have to see what to do it. So flow graph handle, and with this we can call a function, so block ID, port ID, and data. So call block is 0. We could now look at the block at the description of the flow graph and see which block is the HackerF block, and I don't know, get the ID and then from it. But we know it's block 0 in this case, so just hard coded for now. But obviously from the description you could get like search for blocks. You could give blocks particular names. By default, HackerF is HackerF 0, but you can set custom names like my source and then look for this particular block in the description and then address it with this ID. And then the frequency port is, I guess, called frag, and we want to create a U64 PMT with the frequency and call it. So let's see if this is working. Okay, it's at least doing something. Now I can start it, set a frequency. Okay, now it stopped receiving. Oh no, now it rebuilt again. Okay, let's start. It's receiving. We go here. It's not receiving. It's also not erroring. It's already good. Now it receives again. Let's go to channel 11. Oh, it's not receiving. We can now see what happens if we set the device to channel 11. It's receiving again. So it's not just stopping it, but it's actually going to the right frequency. Yeah, pretty cool. Let's go back to 26 because it's kind of the one where it starts with. So see again, stopping, tuning to 26, starting again. Okay, get the frames. Okay. So this was now basically you have everything. You have the way from the GUI to control the flow graph, and you can get data from the flow graph back into the GUI. Back into the GUI. And I guess this is everything you need to to build your own SDR applications in the browser. One thing that we can now do just for fun is, as you've seen in this example, from Trunk, there's also supports Tailwind. Tailwind is a framework. We can, I think it's pretty easy to add some. So to avoid writing any CSS, you can also use Tailwind, which provides you, how is this called? Copy. Tailwind config. And with Tailwind, you can basically, it creates a lot of HTML classes and with specific CSS properties, and then instead of writing a lot of CSS for your own custom classes, no, you just add all these classes to your web components, and therefore you don't have to write CSS yourself. So I will just quickly, let's say I will give it a try to see if I can get this to work now. This Tailwind CSS, we can call this, I don't know. I would say we put this into the assets style. How's this called? CSS. And now we can, in our index HTML, we can add this Tailwind reference. So like they are doing. Tailwind CSS, we have it in assets style. And if it works, we should see that all this formatting goes away to some very basic drilled down styling. Yeah, exactly. And now we can do all this Tailwind stuff. Let's see. Tailwind button. Yeah, just copy paste these classes into our receiver. Where's our button? Here it is. Just give it these classes, or we can go into our index HTML and do beach class. So this I think I don't have a lot of experience with it. I just tried to make something that doesn't look completely strange. Oh, there's something wrong. Oh. And yeah, some people like it, some people don't like it. I mean, obviously you have all these classes here now to format your stuff, but I think it's pretty nice. At least for me, I think it's better than writing CSS myself because I have no idea about it. So at least you can now start to build a website, start to make something that looks nice, and yeah. I mean, with the other examples, I had some very futuristic looking GUI. Maybe I also make it also for the Zigbee receiver, because I think it's great to see, okay, what kind of GUIs you can now easily create. I mean, with the web, now you have all this, it's very easily accessible to build some fancy looking GUI, let's say. But yeah, so this week you focused on the functionality. Oh, let's say start. And even here it would restart. This is one thing I still wanted to show. Now in the start button, you could say in the click method, you could say if the handle is some, we can say already started. Can we return here? Let's see. Or if we do have to add an else branch. Seems to work. Yeah, now if we start, clicked, if we start again, it said already started. So it's not trying to start the same thing up again. Well, for whatever reason, it seems to be always build it twice. I don't know. Anyway, so I guess now we have a complete Zigbee receiver in the browser. We have the GUI. We can interact with the receiver. We can get data out of it. I think that's everything you need to build fancy WebAssembly software-defined radio applications in your browser. So I hope you enjoyed the video. The main thing is, the coolest thing is, I guess, that we now have this develop workflow, which is, I think it's really nice and much better than before. And we don't have this split between mscript and cross-compilation and gluing together these modules, but it's all now in Rust. It's don't have to write one line of JavaScript. It's working pretty well in my opinion, and yeah, so I hope you give this a try. You play a bit around with WebAssembly and FutureSDR and try to build or port over, get some other stuff running in the browser. Okay, so that's it from me. Thank you very much for your attention. See you.